Well, welcome back, everyone. I do hope you all enjoyed your lunch. We had a very busy morning building on what we'd done yesterday. Yesterday, we looked at the control problem, we looked at the fundamentals, and we used MATLAB to construct some simple controllers and look at the properties. Today, we looked at the observer problem. And we spent some time looking in the details of what we need to do to be able to construct an observer. This afternoon, I'm not going to be focusing on how we construct the observer. I'm going to assume that we've covered that. I am going to start with a review of put us back and bring it back to forefront of our minds. Thing we did this morning around sliding mode observers, what they are, what they're good at, what they're not good at. And then I'm going to very much focus on fault detection. So the theme for this slot within the program is very much on fault detection and condition monitoring. So I'm going to make sure that we're all in the zone when it comes to observers and what's really, really important, and recap one or two of the properties that we met this morning. And then I'm going to look at the sliding mode observer problem we had this morning, where we were talking about constructing an observer from the point of view of FDI, fault detection and isolation. And I'm going to look at how this observer gives us a very natural framework to estimate both actuator and sensor faults. So this isn't just saying there is a fault, it's explaining what the impact of the fault is. And we will do that for the pendulum system that we considered this morning, but very much the focus, so I'll present simulation results, potentially maybe for that, depending on time, just so you can have a good idea of how we estimate actuator and sensor faults. And lots of people are using this for a whole range of applications. And at the heart is the design process we met this morning. It's no more, it's doing something clever with that observer, but the design you have to be able to do this, as many people are in the literature and indeed in industry. I'm then going to focus on two applications. One, which is about looking at parameters of systems, which was some work we did with Edwards, who make vacuum pumps for the semiconductor industry. And then I'm going to focus on a very recent study, which is looking at the development of electric power steering systems, where I've been working with my colleague, Marcus Reckartinger, who is at the Technical University of Graz. So this is a joint work with TU Graz. Both of these include real implementations. So these are real implementations of real sliding mode observers, and we will present the results. And then I will conclude our fault detection work. Whoops. Now, as we said, going back in history, sliding modes were all about control. They were all about switching a control, depending on a switching function, looking at system behavior, and deciding which particular control law to use. And effectively, that unit vector nonlinearity for control, which we met yesterday, is doing that. Here is an example. Whoops, I've gone. Let's go back to this. I'm getting confused. Yeah. So here is an example that we saw. We could take systems which weren't desirable. We could switch based on those two systems, and we could construct systems here which had new, better dynamics. And not just are the dynamics improved, but the notion of opening up the class of injections to be discontinuous, the robustness is improved. And when we look at some of the complex systems tomorrow, where we go back to looking at control problems, this will be very much at the heart, switching to do good things in a robust way. And that was what the control problem was all about. It was where everybody started. And we saw very nicely, this summarizes several of the slides from yesterday, where we had the double integrator. We have the pendulum system, which is effectively a double integrator with some uncertainty. And we saw after an initial transient time, both these systems exhibiting the same dynamics. They both exhibit a first order dynamic response, which is chosen from the slope of this line, entirely prescribed by the designer. And the reason we can do this is because we apply a discontinuous injection, like this here, which can be filtered to, when we filter it, we see that it's effectively reconstructing the uncertainty. So we don't know this, but on average, this is constructing this, which enables the effect to be cancelled out for the control. In many control applications, and probably it's why in control, you see applications, but nothing like the number, I would assert, than you see with the observers. You see a long heritage, you see some areas like power electronics, where there are good applications, and indeed where people, I was in Spain giving a lecture not so long ago, people dealing with power electronic systems there, designing these kind of controllers, because the switching doesn't matter. They get the robustness of theory, but actually, for most engineering systems, there would have to be a compromise. You can't have switching. You don't particularly want switching with infinite frequency anyway, which is what theory says we need. And so we smooth, and because we smooth, we approximate. Now, from what we've seen in our MATLAB sessions, that approximation can still do pretty good things. So when we were looking at errors, they were very small, despite the fact that we were using entirely smooth injection signals. So it can be used, but we're not getting what in theory we should be. Now, once we start thinking of the observer problem as we've seen, it becomes, we can relax. It becomes much more straightforward. At the heart of any observer is a model. So you've got some sort of a system that's usually a control system. It's got some sort of feedback in there. We're lumping it in there, all the things that may be going on. So the system open loop, the system closed loop, we're calling it the system. Here we're interested in the observer. So we're interested in putting a dynamical system there, just as we did in our MATLAB block this morning. We added that extra system which seeks to estimate those states, and we call it an observer. And there's all kinds of observers, and you have to be aware of this really when you're comparing what we're doing, because these are different. And if you're talking to people from other domains, observer domains, you will find that quickly the language becomes different. People don't always understand what sliding mode observers do. Why should they if they're not working in that area? Most observers are approximate observers. They try and approximate the states of the plant using the states of the observer. A classical Leuenberger observer comes under that kind of notion, particularly when there is uncertainty present. And for some applications, that might be good enough. We have asymptotic observers, which sometimes can have problems when we get uncertainty. And we have our sliding mode observers, which is nothing to do with the state. Our sliding mode observer seeks to replicate exactly the output of the observer and the output of the plant. So they are identically zero, and any state estimates we get to approximate these will just be a set of states commensurate with this here. And it's natural. We can sliding modes at their heart, and I've been asked several questions on the control problems that we have solved have been stabilization problems. And I've been asked about tracking problems. Tracking problems are no problem for sliding mode controllers. Tracking problems are about forcing an error to zero. Fundamentally, you've got an output. You're not trying to make it zero. You're trying to make the error between it and some output of a model, some reference signal, whatever the signal is that you're trying to track, you're trying to force some error to zero. In the observer problem, you're trying to force the error between the output of the process and the output of the observer to be identically zero. And if you want to zero something, no matter what it is, whether it's to drive a state to the origin and zero it, whether it's a tracking problem and you want to zero an error between a desired position and an actual position, whether you want to design an observer and make the error between the output of the plant and the output of the observer zero, you can't get better than trying to apply a sliding mode technique, because a sliding mode technique will give you zero error in finite time, okay? And it will do it robustly. So it's a very, very powerful technique for making things zero, which is a useful thing to do. And this is what is at the heart of the observer problem. This is why the design, at the end of the lecture, when we looked at the MATLAB, we were asked a very good question about, well, how do we put the poles? And, what about the performance? Well, actually, the performance is fairly trivial. It's make that output error zero. And the faster you can do it, the better. And that's pretty well it. There is nothing to worry about in terms of that design. And the beauty of it is that the discontinuous signal we use to drive these things to zero, is rich in information. So we're applying something which we can switch with infinite frequency. We can switch really, really quickly. So quasi-continuous in terms of being able to switch as rapidly as we like within a software environment. So it's just a model, not the problems of control. So we can get really rich information about what any plant is doing by setting up some sliding mode system. Now, to begin to look at fault detection and isolation, I'm taking the nominal linear system of this morning, A, B, and C. I am thinking of two very specific types of injection here. So this injection here is a sensor fault. It represents something whereby the measurement I'm getting isn't actually the output of the plant. There is something else there as well. So that's a sensor fault. This one here is an actuator fault. Okay? So this is an actuator fault whereby what is happening at the input channel is not quite what we expect. And those are very important classes of problem. If you remember back in history, some of you are probably too young to remember this, but in history a lot of state space methods came about because of the aerospace industry. So the aerospace industry had good nonlinear models before all these other industries like the automotive industry. The automotive industry is there now, but it wasn't initially. The aerospace industry had good nonlinear models. It could linearize those models and it could find state space representations. And for them, actuator and sensor faults are crucial. If there is some sort of an actuator or sensor fault on a plane, then that plane can crash with catastrophic results. So interest in actuator and sensor faults and this marriage with state space systems became natural through history because of that. And then, of course, lots of other systems caught up and started to use the state space methodology too. So the only thing for our fault detection that we're going to do this afternoon, we're going to assume we know the outputs, that we can measure something. And we're going to assume that if there is an input signal that's there, that's driving the system, that we know what it is. So we assume we know the input and we know the output. The sliding mode observer, I'm not going to go into lots of ins and outs about the sliding mode observer. We spent a morning doing that, which I think should be enough for everyone, whether you're interested in the details, whether you're interested in the concepts and you just want to know how to do the design, or whatever level of your interest, we've got lots of information on sliding mode observers. But we're going to think of the impact of this sliding mode observer of the actuator and sensor failure problems. So we're assuming we've got an observer that will generate a sliding mode on this output error y hat minus y in finite time. And the observer is just the same as the one we designed in MATLAB this morning. We're going to have a linear gain here and a non-linear injection that injects into our system something through the input channels. Okay? And we know we can find an observer of this form. We did it based on a linear system so long as we have the rank condition and stable invariant zeros. So we're still going to, at this stage this afternoon, impose these. I'm going to, by the end of the lecture, we'll have done a problem which lifts these away. So the problem with Gratz lifts these away. But at the moment, we're assuming for this development of this general FDI scheme, we're assuming this rank condition holds, and that if we have any invariant zeros, they're in C minus. So I'm going to think, talking about with Sohom before, as we were walking over for lunch, he was saying to me that I think that he thinks the problem with all this is the transformations. We have to get into these heavy transformations to get here. When we're here, everything seems obvious, but it's a step to get into to get the transformations. So we are going to assume we're here for the analysis we do. Okay, we know how to get there for any problem with the transformations, and we know we could implement the observer in these coordinates if we wish to, because it's just a model being driven by y and u. So it's not a problem with using this this set of coordinates. So I showed this morning that this system can be designed to be quadratically stable and that we get an ideal sliding motion on CE, the output error, and that the system stays in the sliding mode. Okay? We notice the actuator fault. And the actuator fault is quite straightforward because the actuator fault is it's just almost like a different name for the disturbance in the input channel. So that's what an actuator fault is. It's a disturbance in the input channel. So in a sense, the problem of designing the for the actuator fault is not such a step. The bigger problem is going to be the sensor fault. Because, of course, if I don't get the output that is the actual output and I get something else because of the sensor fault, I'm going to use that output within my observer, and the impact of the sensor fault is going to propagate through the dynamics. Okay? So, although it seems straightforward, it's not a done deal. So for the actuator fault reconstruction, initially, let's forget. Let's get a bit of confidence. Let's move away from having the sensor fault. So we assume here the sensor fault is 0, and assume we've got this observer which can exhibit the sliding mode as we designed in the MATLAB session. We can see, just as we did for the pendulum with the disturbance signal, we called it a disturbance signal, the same analysis holds. E1 will go to 0, new equivalent will map to something that's related to the actuator fault, and just as we did this morning, we can reconstruct that fault exactly in real time from knowledge of where does script D2 come from. It's just part of the transformation matrix. So this comes from the transformation matrix. This is the size of the switch in the observer. This is the parameter P2 relating to the stable matrix A22S we picked. And here, I may well want to use a bigger delta than I might want to use for the observer implementation. For the observer implementation, I can use delta equals 0. I can use a switch. But to actually reconstruct the actuator fault, we can put in there a value of delta, 0.01, 0.05. This wouldn't be being used to drive the observer. It's just being used to reconstruct the fault. And it can be reconstructed online. So just to make clear from the literature, you sometimes read about unknown input observers. Unknown input observers. And then you see people doing fault detection, and you see them looking at actuator faults, and you think, this looks the same. Well, it is. There are two communities that design of different observers frequently, but they're doing exactly the same problem. They've come from different roots. One's come from a purely fault detection and isolation community. So for signals, for them, they're always faults. Unknown input observers tend to come from more theoretical groups that are interested in observer design for observer design's sake, and they're interested in how we construct observers to estimate those particular signals. So don't be worried or confused when you read things about unknown input observers or fault detection and isolation around actuator faults. Mathematically, as we've just seen, they're exactly the same thing. Okay? So the observer that we could have called the sliding mode observer an unknown input observer. more difficult case now. Let's assume that I don't have this actuator fault. We can see that that's the more straightforward one to do. It makes sense that we can do it. It's just a different name for something we saw this morning. Let's think what happens when we have a sensor fault, so that rather than measuring Y and being returned Y, we actually get something which is the actual Y, which is CX, plus the fault. Okay? This means that within our output error, it's not just going to be CEY. Remember, we take the difference between the output of the plant, which in this case is contaminated by the fault, and the output of the observer Y hat. So we still get CX minus CX hat here, but we have another part here coming from the fault. And that means this is going to propagate into the dynamics. So when you look at our observer error dynamics and you assemble them with this being EY, and noting that EY dot will have an impact from the derivative of the sensor fault here. So F0 dot, that's where that comes from the fact that EY dot, we need to differentiate this here, which gives us an F0 dot here from here. We can see that the actuator fault, the sensor fault, goes everywhere. It appears here in the upper subsystem, and it also appears down here, both in terms of the fault and the derivative of the fault. So the first thing we notice is that if we're going to design an observer, and we could, I've tried to keep the theory down this afternoon, instead of wanted, there are some theoretical bits I want to do, because I think they're important for completeness, and I think at some level we have to understand the framework we're working in if we're going to get the best out of it. Otherwise, if we just assume things are a handle-turning exercise, it limits how we can apply them to problems in the real world. So what we need to do is to make sure the discontinuity here is going to be big enough to counteract these additional bits here. And we can compute, if we know bounds on likely faults and rate of changes of faults, we can make sure it's big enough. Because it's an observer and we don't have to worry too much about having a high gain system, having a big switch inside the system, because it's just a model running in software, then we just make sure that this is large. So we need to have a fairly big switch if we know we're wanting to counteract the faults. Otherwise, what will happen is this won't be big enough to maintain a sliding motion, and any analysis we then want to do to try and reconstruct the fault will be even more inaccurate. There will be inaccuracies coming from the fact that the sliding mode is not reached. So there'll be this part here in there for a start, for example. So if we look here and start to think of what we might get from the equivalent injection, we can see that we can get a relationship, but it's involving both the actuator fault and the rate of change of the actuator fault. And what we do a lot of the time, depending on the fault, is we say that we consider slowly varying faults. So we imagine that F0 is a value, but it's not changing really quickly with respect to time. so that the relative side of this and this are such that this is the important one. So within the dynamics, we can ignore this because the rate of change of time is the rate of change of with time of the actuator fault, of the sensor fault is slow. And that's really common because a lot of the faults that are difficult for fault detection people, so they tell me, are really slow drifting faults. This is a big problem. If you have a big problem with a massive rate of change, usually you can tell by many means. You don't necessarily need a sliding mode observer. Much more kind of difficult is the very slowly varying incipient fault that's in there drifting over a period of time, where for a long time, for example, you might not see any effect at all. And so this assumption of this part being dominant when compared to this part seems to be good enough for most sliding mode, most FDI people who use sliding mode techniques, because they're interested in these that are small and slowly varying and being able to pick them up before something tragic has happened to the plant and you're really seeing it there. So they're assuming that this is small. And so for that, you can actually get some information directly relating the sensor fault from the equivalent injection signal. Now you can see we're going to have to be careful here with what we're saying because we've got inverse matrices here. If we were in discrete time, we wouldn't necessarily worry about inverse matrices, but in continuous time, as soon as we see parts of a system where we're inverting them, we have to think, because we can't necessarily start making inverses. Oops. So here, if we go back here, we have to be a little bit careful. We have to be doubly careful if we're going to write down F0 in terms of new equivalent, because that needs us to invert this whole thing here. And who can say whether that's invertible or not in general? We can say something about it. If we look at a sure expansion of A, so when it's written in terms of its, how shall we say, its script representation, we can see this thing here coming out. So the bit we want to invert here comes out of this sure expansion of the determinant of A. So this will only be non-singular if A is non-singular. And A is often non-singular, is often singular. If you've got an integrator in there, it might well be singular. If we were working in discrete time, these issues are less of a problem. So if we developed a discrete time state space problem, there are results that exist that show invertibility there we're able to assume it. But here, we can't really assume it. But we can get some information, again, by looking at the structure of the rank deficiency. And it's something you may like to do with the MATLAB model we developed this morning. You have an observer. You have an inverted pendulum. You can look at some of these ideas in your Simulink model. You can put in a sensor fault. You know, all it means is in the Y, you just have to add something to it. You can push it through the observer, and you can look and see what you can do here with estimating the sensor fault. So you can see what happens. I'll give you some hints of the sort of things you see. For the actuator fault, we did it. The actuator fault, we distributed something in via B. We didn't actually reconstruct the signal, we just looked at the new equivalent. So you might like to reconstruct the signal and show it what you put in. For this case, you just need to add on a little bit to the output and leave your observer to run. And then you need to look at this matrix and look at the relationship between new equivalent and the fault. And what you actually see by clever looking at the channels, you can see you can get almost everything. So whether you have a sensor fault on the first output, the second output, the third output, you can get all the information from those about those faults in that case by appropriately looking through the channels, when you bear in mind that what you see is one of the channels is effectively giving you the derivative of the sensor fault. Okay? So it's effectively giving you the derivative of the sensor fault. So I haven't done this in the lecture. I wanted to focus on the practical examples, but you should be able to do that, and I think it would be a useful thing to sort of consolidate everything we've learned today, which isn't a big step from the codes I've given you. It's a short job, which I think will give you more confidence with how to do it. So does anyone have any questions about that? Yes? No, yes. Well, this is the problem I said this morning. You know, I haven't said anything about noise here, and clearly there is a problem because one type of thing is an actuator, a sensor fault. Another thing is sensor noise. And depending on the characteristics of the sensor noise, your sliding mode observer may try to track them. So noise is a problem for sliding mode observers. Yeah. In this fault detection framework. Sorry? We will do some examples about this. You mean not an actuator or a sensor fault? Yes, we'll do an example about that now. Yes, well, I mean, ABC matrices are clearly not going to be exact. And we know this morning when we were applying the observer with the inverted pendulum, we applied it to the nonlinear model. The range we were operating over, if we'd have linearized at different points, those matrices would have been different. So, you know, it doesn't matter that ABC is perfect because the sliding mode observer is robust. But it is true, and we will see in the next example, that uncertainty in the model, we do have to kind of know, well, do we need to know? We don't need, it depends on your observer problem. I mean, for fault detection and isolation and monitoring, we're interested in change. That's what we're fundamentally interested in. So long as you've got an ABC which has designed an observer which nominally makes new do nothing, or it can do 2 or 10 or whatever it is, but it does something which is fairly constant and you know relates to good performance, then the discriminator is really change. change in that estimate. So that's what failure detection and monitoring is all about. It's about detecting change. So the fact that you might not have exactly the right parameters at the moment in terms of your model, but you're happy with your plant, then so long as your observer, you get an output error of 0, and you look what the new equivalent is, and you say, well, this is good. This is my plant operating as I want it. The step is, has this changed? Because that might indicate that something has changed in the plant. So I think the nominal parameters for an observer are less important than for controller. For a controller, the nominal parameters impact on the performance of the plant. For an observer, the parameters you assume have no impact on the plant at all. It only impacts on the observer. And so long as you get this y minus y hat equals 0, you have reasonable performance from your observer, it doesn't need to be exact. It's when you start from a point that it's good enough, and you're interested in change. I don't know, what do you mean by an extended state observer? So which papers have you read? Perhaps if you tell me the academic. Right. I don't know, to be honest. I mean, it might well be, at a guess, that what they are doing is they are they're trying to do what we talked about yesterday, like with the integral sliding mode approach, where they're trying to, we've got a smaller subsystem and then a subsystem depending on Y. For me, what they might be doing is trying to estimate all of those states by extending down. But I'm just guessing. I don't know why they have done that, presumably for a state estimation problem. It doesn't make sense, I don't think, for a fault detection problem. Yes, if it's properly designed. Yes. Yes. I mean, it must be said, when we design observers for fault detection and isolation, we don't tend to be using the same observer for control. I think it's better if it's not. But there is nothing to say. I mean, as we said, fault detection observer is like an unknown input observer. Unknown input observers are used in loops with nonlinear controllers to get robust performance. You can do that if you wish. So there is nothing to say they can't be, but many people in sliding mode control don't. I mean, the design overhead, the implementation overhead is tiny. It isn't that you've got some massive machinery to implement it that needs all sorts of analysis and many, many codes and this and that. So why not have more than one? And that is certainly in my group, certainly in Chris Edwards' group as well. A lot has been done on that. It becomes slightly different if you start to consider fault-tolerant control, which effectively means you design in the controller to accommodate the faults. So it's like a robust control that's robust to particular things we know about. Yes.
Then how do you isolate that this sensory actuator is by using unknown input?
Yes. Well, I mean, in this particular case, for our output Y, it was a vector. So we had multiple sensor faults. So there was nothing that said F0 just acted in one channel. And it could be just the same as the actuator. These are matrices. We have a series of equivalent injection signals. you want to be able to map your injection signals onto the faults in each channel, which you can do if that matrix is invertible, the one at the end. If it's not invertible, you have to be a little bit more careful. But there's nothing, there is nothing in what we just spoke about that says you can't have multiple sensor or actuator faults, or indeed have them in many channels. So long as the channels are there, then you can estimate more than one fault. Yes. I mean, a sliding mode observer is an unknown input observer. So it's, we have published unknown input observers. There's a sliding mode observers. It's just a particular type of unknown input observer. Well, it depends on the unknown input observer. I'd say if your unknown input observer was a sliding mode one, yes. If it's a different sort, then you're not going to get exactly the perfect tracking, because you're not going to be able to force things to zero, other than if it's a high gain unknown input observer. To get the same performance from an unknown input observer as you would get from a sliding mode observer, you would need infinite gain. So it's better to have the switch and the discontinuity and the robustness you get from that than to have another type of unknown input observer that to get the same level of performance, you'd need to let gain tend to infinity. But you could do it. It's not saying that you can't do it. People do it. Sorry? Yes, I mean, if you have actuator dynamics in your system, you can look at faults within the actuator dynamics. Chris has done a lot of work on that, actually, for aircraft actuators. Okay, so we're reasonably okay. Some nice questions there. Now I'm going to do my two examples, one by one. The first is going to be a very simple one. And the reason I always present it, it was done a little while ago, but I present it because it's really trivial. It's using the kind of model that a second-year BTEC student could develop. Okay? And yet on a real industrial plant, it does brilliantly. So for me, that's very, very powerful. So we were approached by Edwards, a company in the UK that makes the vacuum pumps for the semiconductor industry. Now, clearly within the semiconductor industry, reliability is incredibly important. If a pump goes down mid-batch, the loss to the company from the semiconductor wafers being wasted is huge. So literally the industry works by having multiple pumps. So what it does is if there is any sort of kind of concern about a particular pump, they take it out and put another one in before they even start. And because it's so important, it's really important to Edwards to be able to show that they are at the front of monitoring. Now, actually, those pumps are highly reliable. They have to be, okay? Because if they weren't, the company that sold unreliable pumps would quickly go out of business. The company that can show it's doing clever things to make sure, however rare it might be to happen, that there won't be a fault or failure, has a competitive edge in terms of marketing. So even though these pumps are highly reliable and they don't tend to fail, They always want to be at the cutting edge of monitoring just so they can maintain their position and say, well, you stick with our pumps, you know they're reliable, and we're doing this research that implements these things that show if there is any problem with your pump, however tiny it is, you will know about it. Okay? So, it's an extreme case, but clearly there is a lot of machinery in industry. So, what we were asked to do was to look at developing some sliding mode observers for their vacuum pumps. For these pumps, because they do lots and lots of monitoring, lots and lots of information is available. It's very sensor rich, so they take lots of measurements already for their monitoring system. So there is plenty of information. So we're not interested in it as an observer that's going to provide state information. They have all that. What they wanted was something that was, like we were talking about earlier, give them that heads up if anything starts to change. So if there is something that starts to change, so not that there's anything that's catastrophic happened, but there is something different in the way a pump is running, to flag it so that at the end of that batch that it's processing, that pump can be taken out, another pump put in, before it starts the next batch. So it's that indicator of very tiny things that may or may not be happening to give you that heads up. So it's using that equivalent injection, just as we talked about, to see a change. Okay, the other thing we need to note is that it's not... it's a fairly harsh environment. So in terms of monitoring, you need something that's really robust. Okay? So when you're talking about why wouldn't you use an unknown input observer, this is an environment where you're going to need to have something which is robust, which of course we know with sliding modes is at the core. And it has to be able to operate all the time. So from startup to operation, and it just needs to say that something is different, that there is something that is happening here and what it may relate to. Here's a picture. We had one in our lab. So they provided us with one in our lab. So here's a picture of the Edwards, of an Edwards vacuum pump. And we were allowed to impose faults. Because these things are relatively robust, there isn't a load of data around about faulty operation. So we were able to adjust the rig. You see here, there are water pipes around for cooling. So in terms of the water pipes, we were able to adjust the flow, to put a valve in there, to adjust the flow in a tiny way so that there was, you wouldn't call it a catastrophic failure, but you would call it a change. So the mass flow rate of water going round to cool the system, we could make tiny changes in that from what would be normal. And we also did some experiments by covering up, changing the heat, because clearly heat is an issue, by covering up pieces. So we modelled it very simply, as I say, second year thermodynamics. I used to do, or even second year control. When I introduced control to my undergraduates in a former course, I don't teach that course at that level at UCL anymore, but I used to model an oven in the kitchen with them. and look at disturbances, look at control for something that everyone knows about. Use very simple heat transfer. This is the level we're at for constructing this model. So there's clearly power going in, there's coolant inlet, there's the pipes going round, there's coolant outlet. We've got temperatures at various points. There's the pump itself and convection to atmosphere. So we used a very simple heat transfer model here. Okay, so we did two sets of equations because we were interested in two types of fault. The first was the temperature of the pump body. So we looked at mass transfer. So we're not using a PDE or anything like that. I've done some work with Sohom since. We could have used a PDE now. We didn't use a PDE then. We just used very simple, very simple approximation. So we assumed the pump body had a particular temperature, clearly affected by the atmosphere, the transfer to atmosphere. It's affected by the transfer to the outside world, and it's clearly getting heat energy as well coming from the currents here. So we can do very simple heat transfer model of the pump body. And the second thing that we did heat transfer around was the coolant outlet temperature. And we could measure all these temperatures. They were all measured within the system anyway. They had lots and lots of sensors on this. So, you know, there were these kind of things, very cheap thermocouples. They have massive SCADA systems that look after these pumps. So they have loads and loads of information. And there are parameters. And it goes back to you talking about the parameters and what are the parameters. We were interested in setting up some nominal parameters that for a sliding mode observer based on these highly known models would force an output error, the temperature output errors, to 0. Okay? And we wanted a new equivalent that would be reasonably constant in nominal conditions, and we wanted to see how sensitive it would be to changes in some of these parameters that might be indicative of a fault. So here we see all these things are measurable. Masses we can measure, areas we could measure. We could approximate these to parameterize for nominal operating conditions. And basically, my student did that. We did some experiments in the lab, and we looked at being able to get a decent open-loop model. I'm sure not perfect. But we looked in terms of our one fault, which was if there's a problem with the coolant system. So if there's a problem with the cooling system, it's likely to mean that the mass flow rate here changes. Okay? Otherwise, there won't really be a problem. If cold water can carry on going round in a normal way, there's not going to be a problem. So the mass flow rate, we looked at having a nominal mass flow rate and a change in the mass flow rate. So we were looking at being able to detect changes in the mass flow rate in the pump. And the other thing we were interested in was the heat transfer coefficient. So we were looking effectively at how the pump was managing to deal with getting rid of the heat of the block, if you like, of the pump. So we took deviations here from nominal in terms of the heat transfer coefficient. And we wanted to see if we change the valve on the water flow, would the new equivalent give us, would it tell us that this had happened? You know, clearly you can see if there is a problem with temperature, with the pump being able to cope with getting too hot, there comes a point when you know. If you look at the temperature itself, you can see, goodness, this pump has got too hot. We're looking at the stage before that, where the parameters of the system start to change, long before we have a catastrophic fault. So we use very simple sliding mode observer. We did just as what we done this morning. We wrote down an observer here, which was the nominal dynamics. We used a linear injection, and we used a discontinuous injection. So the beta parameters, rather like the A22S this morning, provide asymptotic error decay. This discontinuous injection makes sure we can attain a sliding mode. And then we can look at the difference between the two to try, so the observer and the plant, to try and get some knowledge. So here we see that for our injection signals, for a model that's parameterized around nominal operation of the pump, remember it's a steady state operating, steady state machine. Okay? So we see that changes in the mass flow rates here come from this first detector signal. We'd know if it was a problem with the heat transfer coefficient because only this signal here would be affected. Okay? Only this signal here would be affected by the heat transfer. So we implemented this observer. This shows the pump on startup. And so here you've got the temperature of the block and the observer estimate of the temperature of the block. You can see they're visually identical. So even during the startup phase, she starts ambient. This is ambient in the UK. Probably wouldn't be ambient in Roorkee for much of the time. But it comes up and they're visually indistinguishable. You see the errors here, incredibly small. Incredibly small. So we could attain a sliding mode very, very well. We did some experiments here. You can see initially the observer needs to converge. So we do see the convergence. This is looking at new equivalent, and it's looking at the change in mass flow rate. So we can see it doesn't do anything much at all. And then we change the valve. So we turn the valve slightly. So the coolant flow rate round the pump has changed. And we can see very quickly it picks it up. It shows that the mass flow rate within the cooling system has changed. Then we turn the valve back off so that it goes back to normal operation, and it goes back up. Okay? So for very, very small changes, we can actually look at changes in the parameters. And based on this work, we went on to do more work, which was also with another steady-state machine. This was with a company called Perkins. They make systems that can be used for power generation. They can be used for power generation in areas of the developing world. So they might, for example, be used to run mobile phone networks in remote areas. They're also used in big agricultural machinery, so another very harsh environment. where also people might be quite remote and where you're not necessarily going to have an engineer on hand if something goes wrong with them. So they make big engines. They were interested in being able to monitor these parameters, monitoring these changes, again in steady-state machines, so that they could look after the kind of, how shall we say, the support side of their business. So if you've got these machines out running mobile phone networks in very remote places, you need to coordinate when people are going to be available to go and sort out a problem. What you don't want is for the whole thing to collapse and it to become a critical situation, and everybody is cross, the situations may not be safe. Likewise, you're a farmer, you can't carry on doing what you're supposed to be doing at what may be a critical time of the year. You want to have that knowledge up front, rather like we see on our cars increasingly. I think my car is cleverer than I am these days, so that it can tell you when it's got a problem. And this is what they wanted, very small changes, so they know, well, this hasn't broken yet, but I should be on the lookout that I may need to send off one of my engineers to XYZ site because something is beginning to change. So it's very, very good at that. And you see, the actual parameters don't matter in those cases. The actual parameter, you've got a steady-state machine, you're interested in having a nominal representation of it, and you want to know if there are changes, fundamentally. So that was what that problem was all about. So I don't know if anyone's got any questions about that one before I go on to the next one. Okay. Well, the next one's a little bit more techy. That one was very simple. The model was very simple. The model isn't difficult here, but we're going to use some additional concepts of really feeding towards tomorrow, which I always think is a good thing to do when you're running a course, to give a sort of view of where we're going. We were trying here to design an unknown input observer, which was a sliding mode observer, to enhance the driver experience of electric power steering systems. Now, me, in the UK, I learned to drive on a car just like this. You turn the steering wheel and you were physically turning via the steering column the steering rack. So it was a job, you know. You were doing it yourself. And it's heavy. These days, probably, as I'm older, it would be harder than at the stage when I was learning to drive. But it's effectively, you're moving a mass by steering without any assistance. So in order to give assistance to help people, and, you know, the good reasons to help some people, but probably now it's becoming more the norm, they developed hydraulic power steering systems. So effectively, there's some hydraulic system which helps you with steering. Okay, I did too many. This has some drawbacks, though. It's heavy on power, and the implementations that we have aren't suited for modern assistance systems. So vehicles now, we're beginning to think of how we put like lane following into those systems. These hydraulic systems don't mesh well with those systems. This is important for systems integration. You know, as far as the automotive industry is concerned, it's a complex system. A complex system, when you develop things, they have to be able to interact easily with other things. If you've got the best bit in the world and it doesn't work very well with everything around it and it doesn't fit well, nobody's going to be interested in using it or buying it. They're not going to change everything else just to fit your component. So this had some problems. So because of this, the industry started to develop electric power steering systems. So it replaced the hydraulics with an electric motor. And the electric motor can either be here on the pinion, or it can be here on the steering wheel. So there are different configurations. This is just a schematic. So I'm not saying that it has to be here. It's in different places, different motor manufacturers. And it's good. It doesn't use as much power as the hydraulic system. It fits very nicely into the architectures of these lane-keeping systems that they're wanting to implement. It does have a big disadvantage, though. And this disadvantage, I think, illustrates the way control is going. And it's important for complex systems and the kind of systems we're going to begin to think about, the kind of problems we have in the future around control. Nowadays, when I started my career, as I told you, in the aerospace industry, I was designing control systems for combat aircraft in the UK. And I then became an academic. And in some of my early academic problems, I was working with automotive systems, even then. So I've had a long time working with different automotive systems. But at that time, it was very much at the element level. Might be an electronic throttle controller. It was a spec around a very small element of a vehicle with no consideration of how that element interacted with other subsystems. But most importantly, absolutely nothing in the specification that said, do people like to drive with this controller? How does this electronic throttle feel? Whereas the space we're moving to now for controller design is all around cyber-physical and human systems. They're bigger systems, which makes them complex just because of size, but they're not just bigger. They're also more complex because of some of the things, the elements we now have to consider, which we didn't used to have to consider. And this is an example of one of those. Because this, as an engineering solution, it solved the problem. It has a problem, though, in that people don't like it. So if people are out driving their... And if you think of from the point of view of a motor manufacturer, people are going to buy their cars because they like it. They're not going to buy it because you say, look, this is really good. You know, you don't need to expend all this effort, and it's much more energy efficient. It's not going to go. It's not going to fly. And its big disadvantage is its poor road-to-driver feedback. It's very good at what it's doing, but the driver has no idea. And clearly, it's important for a driver to know what's going on. Otherwise, we get unintended consequences. Drivers overcompensate because they don't know they see something happening, they think, gosh, I should be doing this. They don't know what the actual ABS system, for example, is doing for them. And this was illustrated, it must be said, this is due, as you can probably see from the link, this was very much due to my collaborator, Marcus. I'm not a big reader of car magazines, but this actually shows the problem very, very nicely. It came in a magazine article all about power steering systems. And these were professional test drivers, so the equivalent of the pilots that in my old career used to fly the planes, the test pilots that used to comment on the controllers. And you can see at the top here, in the sort of funny greeny, olivey colour, that is the electric power steering system. In the more jade colour, at the bottom here, that is the hydraulic power steering. And so in their benchmarking, they scored over a number of these drivers. And you can see that when it comes to on-sensor sensitivity, effort, linearity, precision, quickness, this electric power steering system outperforms the hydraulic power system. So everything they're happy about. But there is a big problem. The feedback to the driver from the system was didn't do well. So it was found to be superior in 7 of the 10, but all of the 3 relating to feedback, it did worse. So people liked this highly inefficient power steering system. So coming with that, and here you see I've moved my assisting motor to show I can. It's now on the it's now here on the steering column. Became the need to estimate some signals. To estimate some signals here to be able to be used by the power steering controller to be able to give the driver a better handle on what was actually happening, particularly out here. There's nothing worse. You know, and we all know, you probably have, I don't know, because living in India, you may not have driven on ice. I rarely get to drive on snow and ice, thankfully, because we live in the southern part of the UK. But when you do, and the car does things that you don't expect it to do, it's very difficult, even though I know the physics, not to overcompensate and respond and do something, because you feel something, how it's nature, isn't it? Something happens, we should try and protect ourselves. So what we're trying to do is take sensors, things we can measure, like the steering speed, the column torque, which are measured on the vehicle, and we needed to do this on a real vehicle, and use an estimation signal to get signals here relating to the thing which is going to give the driver feedback through the action of the controller so that they know what the EPS system is doing. It's a really simple system to model, so it's not a difficult system to model. Again, you can use rather basic mechanics to write down what is a relatively low order model. We have our sensors, angle and angular velocity sensor, and we have our torque sensor. So we know what they are. The 2 things we want to measure are TD and F, coming up there in red. So we started a bit like we started this morning, writing down a model. So we defined some state variables. We wrote down a state space model. We had the input signal, which was known. We had the disturbance signal, which was not known. And we had some things we could measure. We then started to do an observer design. If you look, that's just in the form of what we had in our lectures. So we had a look at it and we saw, can we use the existing tools? Can we use the approach? What are the transmission zeros? What about full rank, etc.? And we checked, and the invariant zeros are stable, so that was good. But the matching conditions didn't hold. The things we're trying to estimate don't channel into where we can measure. So we can't use the existing tools. And this is why I want to encourage you not to be limited by what I've told you. You know, as we get to, and this isn't, in terms of size, all right, there's a human in the loop, but in terms of size, this isn't the most complicated system in the world. And already we need to be creative. We need to think and plan and design. I always say to my students, being a control engineer is as much of an art as it is of a science. We need our scientific roots, but to develop solutions, we also need to be creative. We don't want to try and fit problems into a box and say, right, this is the box. This solves all these problems. We just put this in and out comes a solution, because that isn't going to work. We'll talk a little bit more about this tomorrow, but this recent IFAC report on the future of control, this very much says this, that systems and control specialists need to step back further from not being the individuals who just stand there and apply a tool for a system designed for other purposes. We need to move back into the problem and think about how we can build different systems. And this is a small example of this. So the first thing we notice, taking a step-by-step approach here, where I'm not meaning a step-by-step observer. For those of you, I'm just meaning that we just look at one thing at a time. The first state variable is actually measurable. It's the output here, okay? It's the first output. And this here, one of the signals we're trying to estimate to give our driver feedback to the control system, appears in these dynamics. So for this subsystem, we can design an observer. And we did. We aren't using we're not using a classical sliding mode control injection. This is effectively a twisting type injection to feed into what we did yesterday, what we're going to do tomorrow. But effectively, this is an injection which will zero the output error y1 minus y hat. We can write down the aerodynamics, and by forcing those aerodynamics to zero, which we can do, this signal here is bounded. We can show that in finite time we get a sliding mode, and we get a signal here which directly relates to one of the signals which is unknown. So we can estimate TD. We can put a green light there to say we can get it. What happens when we look at the second output? Well, the second output that we can measure, we can see the signal we want isn't there. Okay? The signal we want is not there. And this is why the rank condition doesn't hold. Okay? There is no mapping from the output here to this signal F we want to have. But there is something there that we need to have, which is X2. Okay? So we said, well, the rank condition doesn't hold, and so we can't get F from Y2, but let's get what we can get. Let's get X2 from this observer. So away we went, designed what's a higher order observer, got finite convergence time of E2, and managed to get X2, which was an added bonus. Okay? So we had X2 now as a signal exactly from our observer. We now got X2, so we said, well, having got X2, why can't we use the X2 we've got and use the second state equation here as an equation to estimate F? Okay, because here is X2. It's not one of the measured outputs, but we've used our observer as a soft sensor to get X2 hat, if you like, an estimate of it. And so we can use that to reconstruct F. And that's what we did. So we used that. We saw finite convergence. We managed to reconstruct F. And then we went to test. So this is on a test bench. This is actually a Mini Cooper. I don't know, do you have Minis in India? They're made by BMW. They're quite popular. I don't have a Mini Cooper myself. I have a Mini one, a cheaper one. But so this is a Mini Cooper, and it's using the sensors from the steering system. So this isn't using, we haven't put additional sensors in. to implement our observer. We're using the sensors that are on the system, but we have implemented, if you like, some additional stuff here. So this here, spring damper, is effectively reconstructing the tyre force. Okay, we can't obviously put this on a vehicle. It would be quite dangerous, or much more dangerous than doing it on a static rig. But we can apply the forces as if it was driving by a different system. So we put a spring damper on the system here to generate the tyre force that would come. That tyre force comes from changes in the road conditions. We obviously aren't moving on the road, but we're doing that. And we can estimate that, so we know what that is for our rig, so we can tell how well our observer does. We used a controller. Clearly we needed to have a controller on this system, so we used a controller that was already on the rig. We did some simulation results, and as we've seen, when you use computers, you can do very aggressive things. So this is simulation. This is the steering angle, so you can see very actively through large numbers of degrees, very quickly moving around. And this gives you an idea of steering torque. If you look at the estimation errors, you can see here that they are small. So x2 minus x2 hat, TD minus TD hat, the estimated force here and the rack force are tracking very closely. We've heard some things about parameter estimation and using variable gains on our switches. We did use a variable gain here for kappa 5, and so this shows what kappa 5 was doing. To do the experiments, we couldn't be quite as aggressive because you've got to physically, the thing has got to physically move, but we're still going through quite large transients over relatively short periods of time. And you can see that the estimated TD that the observer gave us compared to the TD we could measure on the rig, the estimated F compared to the measured F, because it's a rig, we can measure it. The estimated X, the measured X, you can see very good tracking. So these are real experiments. We're getting very good tracking. The only one where we're slightly off is the F. And, you know, it's a question as to whether F is the real. So it's still very, very good. And it still gives you a very good idea of the force, the tyre force, what's happening at the wheels in the system. So I'm hoping with what we've seen today that sliding mode observers aren't difficult to design. I mean, you know, we have the codes for the straightforward system representation from state space. I'm sure you will have seen what we did with the vacuum pump. The one that we used for this particular parameter estimation problem, it's slightly more involved. We're going to learn more about that tomorrow. But I wanted you to see it in action because that hopefully will make you keener to learn about it. But we can get nice output errors. It's a natural design objective. It zeroes something. And that's what sliding modes are really good at. We don't have any problem with chattering at all because this is sitting on a microprocessor. And we can use this equivalent injection principle, as we've seen, for all sorts of problems. It really is a positive thing for finding out information about systems. It runs in real time. It's being used by industry. I think the results on the design of the EPS system for a vehicle are very convincing. I'm working with Jaguar Land Rover, who you may have heard of. We're applying some of these observers for a range of problems for them, for ABS, whole vehicle, lateral stability control. An estimation related to those problems. And we're doing it without using masses of measurements. My message to you is information these days is relatively cheap for most purposes. And if you haven't got a measurement, then rather like we did with the EPS system, why not use a soft sensor? Why not use another observer to generate what you want? We have at the fingertips the means to construct measurements. And increasingly, I use soft sensors, as we saw with Marcus, which then means we have no problems with satisfying those particular conditions. And the differentiator we learn about tomorrow, that will be another means whereby we can get rich information to use for these kind of systems. So I think that was all I wanted to say. I don't know if we have any questions about those examples. Sorry? Yes. So I wasn't using a classical, largely because, I often don't use higher order sliding modes myself. So, I think with most things you can do it with a conventional first order sliding mode. But my collaborator uses a lot of higher order sliding modes. So for that one, we were using the super twisting algorithm, which is a second order sliding mode controller. Or a second order sliding mode injection, because we're using it as an observer. We will see about that tomorrow. Effectively what that is an injection that doesn't just make S equal 0, it makes S dot equal 0 as well. So the only difference between classicals, everything we've done up to now has, until we saw that EPS system, we just made S equal 0, and the discontinuity acted on S dot. We can have higher order sliding modes, where for a second order sliding mode, we try and make S and S dot both equal to 0, and the injection signal effectively acts on S double dot. And this was a particular second order sliding mode controller, the super twisting algorithm that we applied here. But that will be at the heart of what we do with the differentiators tomorrow. Sorry? Yes. And if I'd done the simulations, probably it would have been. Marcus did the simulations. So but yeah, as we saw, the structural conditions are there. We could have forced a sliding mode with the simple type of injection such as we've been using today. Any more questions? I didn't fully understand the question. I think what you're saying is if you use an estimation method to construct a signal, how can you use it in the control system? Well, you can use it by feed-forward injection. That's what feed-forward control is. Feed-forward control says we know the signal. And so if we know any signal, the problem with feed-forward control is frequently we don't know the signal. But if you have a reference signal, frequently you would use a feed-forward component, wouldn't you, of the reference signal within your controller. So we would do exactly the same with the estimate of the disturbance signal that came from the unknown input observer. Does that answer the question? Sorry? Yes. Yes, definitely. Yes. 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 Yeah. And indeed, that's one of the problems I've been very interested in, is how we take those higher order systems where they might very well be all interacted together, but how we make sure the overall system stays stable despite the interconnections. We've seen huge problems. I mean, what happened internationally in the banking system demonstrates what happens when interactions flow through a complex system. The problem with that happened there in a very simple sense is the banking regulation said, well, if every bank has enough money, and so if all the subsystems are conservatively enough operated, then if one bank has a problem, it won't propagate. And clearly that was a massive issue, and it wasn't true at all. The interconnections were such that it's fine if interconnections are small, then perhaps to have conservatively controlled elements is sufficient. But when the levels of interconnections are higher, and clearly in our society it's very interconnected internationally at every level, interconnections are big. And when things are interconnected, you need to be able to use the properties of the interconnections to ensure you maintain the stability. So one could argue that the regulations that prevented banks from trading at the time of the banking crash, actually it would have been better if they had been able to trade, because as it was, it just all propagated and many, many banks and industries were affected, and individuals indeed.